In this video, we're going to look at how choosing different initial values can lead to some perhaps surprising results. We're going to start with what we have already, W10.3, and save it as a new file because we're going to be breaking some things temporarily. So we'll save that as W10.4. And the main change at the outset is just to make all the positions to be the same. In other words, we're going to lump all of our dots right on top of each other. We know that the length should spread out. So let's just see what happens. There's no reason for us to have to think so hard about these initial conditions, right? Let's just make them all ones and twos, or ones for both of them. Why not? That only affects where we start in terms of our configuration. And if we run this, we see that fmin search pushes things away from each other, as it should, and it does some nifty things in terms of scaling. And gradually it's heading towards lower and lower energy. So, it's taking longer, but it's working. It's doing its business. It's a little jittery. We'll give it a few more seconds here. There we go. Now we're getting into lower values for the energy. It's honing in. And we should be able to get down again to about 10 to the minus 10 or so, I'm guessing, before this finishes up. There we go, 10 to the minus 9. Starting at all the same position, which is a pretty lousy initial starting value, but it still managed to search its way through that and find a configuration that had 0 energy. Beautiful, did its job. Now, let's try the same thing, but with fmin-unc and see what happens. Again, these are hot swappable search algorithms because they have exactly the same input structure. fmin-unc. This was the jitter things, jump around, don't worry too much about slopes. This one is based on the gradient methods, has some pros and cons to it. And that's interesting. Notice what it did and notice what its final energy value was. It had a hard time working with that because it wasn't able to find a 0 energy configuration. You can see it did something weird, or unexpected anyway, trying to force everything down a line. Now that comes from the underlying derivative calculations that it's trying to work with, and that not being a great idea if your initial configuration is lousy. This initial configuration, all of the nodes right on top of each other, is definitely not even close to the right answer. Sometimes doing that kind of assumption of let's just put in all zeros, all ones, is not going to be the best approach. The optimizer can overcome a lot of things, but sometimes it'll actually break down the search. It'll give you a suboptimal result, one you know it can do better than, but because you chose poor initial values far away from an optimum, it just falls into some local trap. How do you fix it? You just get better initial conditions. So values we had before were something like this. Just kind of lay them out at least something like in a circle. Let's see what that looks like. So moving left to right and then having a couple values down lower. If we do that, then fmin-unc is lovely. Does a wonderful job. In fact, if we look at it, it only took 9 iterations for that to get a super high accurate energy configuration, low energy configuration. And it was beautiful. All because we chose better starting values. So don't forget that lesson. The closer your starting values are, the better fmin search or fmin-unc will do in terms of being able to locate a minimum. Here's fmin search doing that same search, but from those split apart starting points. And again, we can see it's doing a better job earlier on in the process. It's only going to take about 300 iterations here instead of the 600 odd it took before. So good starting values are worth their weight. There's a quick summary of those notes, but there's one last thing we want to include as a practical tip, and that is in case you have poor starting values that lead to slow improvements, you'd like to be able to stop and freeze frame and capture what you've had so far. The way you can achieve that is using the optimset command, including the display iter is useful, but you can also let it know that you want to do a maximum number of iterations, say 500, or in this case here, we saw performance not really change much after 200 iterations. So what you can say is, I would like to only do 200 iterations this time, please and thank you. And it'll search, it'll search, it'll search. Notice the iteration count is here. And once we get towards 200, well, in fact, exactly at 200, it's going to exit, and it's going to tell you that the maximum number of iterations it knows about has been exceeded. And now VOPT is actually holding the values that you're seeing on the plot here. So you have the best values so far after those 200 iterations. What some people like to do, and it's not a bad approach, is to loop around this, search for a certain number of iterations, take your VOPT, and then use that as the new initial conditions for the next search. So you're basically saving every 200 steps along the way. And that can be powerful if you're running multi-hour searches and you want to be able to stop at any point just to check in on how things are going. If you have this at 5 million, then the search can go on for a long time. And if you have to cancel it or your computer runs out of battery, you've lost all that work unless you've been stopping it regularly with a maximum iteration count and storing the optimal values you found so far. So that's one last little tip for the optimization side of things. And that concludes our videos for the course.